You're listening to Let's Talk AI.
Okay, good day. Welcome to Let's Talk AI. Today's guest is William Melek. William is a professor in the Department of Mechanical and Mechatronics Engineering at the University of Waterloo. He also serves as the director of the Laboratory of Computational Intelligence and Automation and the director of the RoboHub. So, welcome, William.
Welcome, Harold. Thank you for having me.
Awesome. So, William, before we launch into your background and how you're using AI and the RoboHub, etc., University of Waterloo has a unique breakout between mechanical engineering and mechatronics engineering. Could you explain what is the difference on the mechatronics side?
Yeah, that's actually a very good question, Harold, and I'm happy you asked that because we have one of the most established mechatronics programs in Canada and probably the oldest too. It's been in existence for about 20 years now. So, in a nutshell, actually, mechatronics is a newer branch of engineering by comparison to the traditional engineering disciplines, where actually graduates combine knowledge of mechanical, electrical, information technology, and precision machining in order to be able to build advanced electromechanical systems. So, key application areas involve building robots, building surgical devices, building wearables, technology for smart devices, as well as many of the technologies associated with deployment of autonomous systems and electric vehicles.
Excellent, excellent. So you're the director of the Computational Intelligence and Automation Lab and the director of RoboHub. Give us a high level on the computational intelligence and automation, and then we'll do a deeper dive into RoboHub.
So the Computational Intelligence and Automation Lab focuses on conducting research on advanced flexible type of robots, which are typically robots that you will begin to see more and more as part of advanced manufacturing and Industry 4.0, but they tend to be more agile, more intelligent, and collaborative. So they do require more advanced design of motion planning, situation awareness, precision control, and all of the above actually requires implementation of one form of machine learning or artificial intelligence in order to be able to enable the system functionality. So I mean there are kind of they go hand in hand. The research that we do with the Laboratory of Computational Intelligence and Automation, advanced robotics and controls on one hand, artificial intelligence on the other hand, and then we use these tools to build systems and robots that can work in a human-centric environment for the purpose of deployment in new paradigms related to Industry 4.0 and advanced manufacturing.
Okay, so before we launch into RoboHub, let's back up a little bit and learn more about this guy named William. How did this all start for you? Undergrad, master's, PhD. Where did you do your studies?
Oh geez, okay. So let me kind of again go back. Bachelor's was of course overseas in Egypt, and I earned a bachelor's degree in electrical engineering in the mid 90s. And then shortly after, I worked actually with Siemens after that for a couple of years, but I still kind of wanted to learn more about robotics and perhaps be able to kind of test my hands in research. So I applied for several schools in Canada, the United States, and I received admission to come to University of Toronto. That dates back to 1996 with the Department of Mechanical and Industrial Engineering, and that's where I did my master's degree there, earned the Masters of Applied Science in robotics. And then I decided to continue after that, maybe fast track to hopefully get the PhD quickly so that I can kind of pursue a career in research and academia. So I continued in the same school but in a different department and did my doctorate degree, which did actually involve research in robotics, but was my first introduction also to advanced AI because I had to apply this to my thesis projects. I earned a PhD degree from the University of Toronto in 2002 and then worked as a research director for Alpha Laboratories in Toronto for 2 years before joining the University of Waterloo in 2004. So I've been with U of T or UW probably about 18 years now.
Okay, that's great. So I know, anybody who visits campus here in E7 and sees the RoboHub and it looks like this big glass enclosure and all these robots. Can you tell us a little bit about how did this start? What was the journey to bring RoboHub to creation, and a bit of the framework there, and then we'll dive more into what's going on inside the glass.
So being actually the largest engineering school in Canada in terms of undergraduate student population and the size of the faculty in terms of researchers, back in 2016, I realized that there are about maybe 40 of us across different faculties conducting research on robotics or closely related areas. And we wanted to kind of consolidate the robotics research because many of us were collaborating, but we didn't have a framework or kind of an umbrella that kind of enabled us to do this in a more seamless and manner and be able to kind of have this continuity in terms of tapping in on the expertise of different researchers on campus. So we came up with the idea of having this new facility which will house robots, all different types of robotic systems, and will be actually the catalyst for many of our colleagues and industry to engage with the Faculty of Engineering at University of Waterloo, promote collaboration with industry, promote collaboration among faculty members, but also create this advanced facility for training of our undergraduate and graduate students on the basically most advanced and up-to-date technology in robotics. And we formulated a project that dates back to 2017, and at the time I had there were six of us. I was leading the endeavor, and I had five of our colleagues from three different engineering departments with me, and we made the submission to the Canada Foundation of Innovation. With matching from the Ontario Research Fund, and fortunately for us, the proposal was successful. So we were awarded at the time about $4.5 million in funding to start the RoboHub, and for the period of about a year since we received the funding, we were working in parallel with the architects and the engineers who were in charge of the new building, which was E7, because we had the again like the crown jewel space on the ground floor. So we had to coordinate with them, and the lab officially opened in October of 2018. So we've been in existence now for about 4 years, but actually the period of productivity was slightly less than 4 years because of some of the setbacks we had during the pandemic, which did require for us to lock down the lab for an extended period of time.
Okay. So, myself coming from industry, robots were always, shall we say, in cages. They're zipping in and out of injection molding machines, processing equipment online. The RoboHub flavor seems to be somewhat different. I don't see any cages, more collaborative around humans. Could you elaborate further of, what's the theme, the high level, like what's the goal of RoboHub?
Actually, very good question, Harold. I think the general kind of premise or theme of the RoboHub here is to create this fleet of heterogeneous intelligent robots that can be deployed in a human-centric environment, work close to humans without the need for caging or fencing. But that, of course, would require for the robot not only to be a pick-and-place tool or a packaging tool that basically does not have any capabilities of situation awareness, but instead now migrate to intelligent robots, or what we call them in industry and the scientific community, cobots. Cobots is short for collaborative robots. And of course, you look at these systems, you begin to realize that they have a very rich sensing, they have advanced processing, higher level control to enable interaction with human, to enable understanding human gesture, understanding human commands, whether it's in gesture or speech, but also advanced vision and image processing to be able to locate itself within its environment, understand what are the objects of interest in the environment, and then interact accordingly to be able to do the tasks safely and efficiently. And I want to re-stress the point human-centric environment. So we want to bring the robot and the human close to each other. They work in close proximity, and in an ideal case scenario, are able to collaborate seamlessly. And of course, that kind of philosophy for design, control, and deployment of robots would basically necessitate the removal of the fencing that you would typically see in all the industrial robots, the fencing that separates man from machine. So that actually is something that most of the research activities and industry projects we have in the RoboHub is moving away from this paradigm and making sure that we can bring human and machine as close as possible to each other in a safe and effective manner.
Okay, you set the stage earlier, and you said in 2016 we had about 40, separated researchers in robotics. So here we are now in 2022 of October. How many researchers are we having doing, primary researchers, PIs doing robotics, and then how many grads under them, just roughly off the top of your head?
I think at this point in time, again, off the top of my head, I guess, Harold, we're kind of in the neighborhood of 60. And then, of course, the level of activities when it comes to robotics research varies, depending on whether the primary area of research is AI and the secondary area is robotics, or the primary area is robotics, or maybe they are working primarily in fields that are complementary to robotics. So, for instance, path planning, controls, optimization, and people who work in fundamental AI as opposed to operational AI. So off the top of my head, I think we are 60. And in terms of number of graduate students, by the last count I had, which is about 8 months ago, I would say roughly about 250 graduate students from three different faculties.
Wow, that's great. So you mentioned the magic word AI, and previously you talked about vision and voice activated robots. From a high level, just give us some structure here. How are you using AI in the lab, and where is that going?
Yeah, that's actually a very good question, Harold. So again, it's a multifaceted actually approach when we rely on AI to be able to power or enable a lot of the research activities we have in the RoboHub. One aspect of it focuses on using machine learning and in particular the new advancements in convolution neural networks and deep networks for basically more accurate image processing and object classification in the three-dimensional space. And we use this type of AI to create this situation awareness for the robot. So we are able to equip our all of our setups with machine vision, and then obviously through the images that are captured, this goes into an AI engine which begins to classify the environment for the robot, identify where objects of interest are, identify where obstacles are, and inform the path planning and the next stages in the pipeline, which is how we're going to control the robot to complete the task that it needs to in a safe and efficient manner. So machine vision is part of it, but now after we've kind of located the robot within the environment, the next step is to create the path for the robot, and it's a collision-free path. It's a safe path that also is within the confines of what the human or humans would like the robot to do, and that would involve a lot of non-conventional optimization. So we use several optimization techniques that basically rely on concepts like genetic algorithms or simulated annealing, and the kind of the optimizations that kind of fall under the realm of this type of AI, mathematical AI models. Now, once we've identified the optimal path, the next step is to begin to have the robot execute the motions in a manner that is controlled. And that control also where we bring in again artificial intelligence in intelligent control, whether it's a neural network control or a neurofuzzy control or any other type of advanced control that will allow us to create this level of precision but also compliance, because some of these machines we don't want them to exert excessive force in the workspace, damage a package they are handling, or maybe cause potential injury to human. So the compliance and this type of force store control does also entail artificial intelligence. So again, that's an example of three specific areas where we rely heavily on AI to add this functionality into our system, this advanced functionality to enable the man and machine to work in close proximity to each other. Of course, there are other examples, but I think those three are the key ones that come to mind at this point in time.
So, for your average person, if they think about robots, sadly we jump over to memories from Terminator movies and things like this. But the definition of a robot is so much broader now. I mean, with drones and all these other aspects, what kind of robots do you have in RoboHub?
Actually, you would be surprised, Harold. We pretty much have all different platforms I would actually venture to say that it's a one-of-a-kind research facility in terms of the variety of robotic platforms we have. So we have different platforms ranging from very advanced humanoid platforms that are very high degree of freedom, similar to the setup that Boston Dynamics has, or the Valkyrie system that NASA uses, but also having a small type of humanoids that are used primarily for early childhood education or maybe companionship, so like a pet, and they can converse in 22 different languages, and they have some simple AI for speech recognition, just very simple phrases. But we also have a large fleet of industrial arms, robotic arms, which are basically the next generation of the fenced robots that you would typically see in industry, but they are designed with the collaborative nature in mind. So they tend to be smaller, more agile, high number of degrees of freedom, and they don't have the sort of speed or the strength of the industrial robot, but they are designed with the human in mind. They can collaborate with human, and they have different stacks on the software where you can control intelligence. We also have a big variety of drones for indoors and outdoors research, primarily used for mapping and very popular among our industry partners, whether they are in agriculture, city planning, inspection of maybe crops or roofs of buildings, and all the way to advanced situation awareness scenario with our military subcontractors, General Dynamics, Lockheed Martin, Leonardo. We also have mobile platforms, and the mobile platforms enables us to conduct research, which kind of feeds into some of our autonomous vehicles research. But of course, differences are a vehicle platform is different from a mobile robotic platform. So those are typically used to conduct research related to moving of objects, maybe in mining, but in supply chain and warehousing, and even with some of our industry partners like Avid Bots, indoor cleaning robots. And we also have magnetic levitation robotic systems, and those typically are used to transport material within an indoor space at a very high speed and completely frictionless, so very energy efficient. And they rely on the same concept of the maglev trains that travel between Tokyo and Osaka, cut the 500-kilometer distance in 90 minutes. So it's the same concept. You kind of float capsules in mid-air. They travel on tracks under very kind of narrow air gap and very precise control at very high speed. So imagine a fulfillment center for Amazon. You can get a package from one end of the warehouse to the other end in 30 seconds. Cut that distance. So I mean again, the beauty that we have here is that we also in the RoboHub also work on robot operating system and other kind of operating system platforms that allow all of these robots to communicate with each other, form a team to conduct very complex tasks, even they are if they are on different platforms or coming from different vendors. So that's in a nutshell, actually, the key capabilities that we have in the RoboHub and the different variety of robotic systems we have there.
Well, you and your team are with a huge serving of patients. I swear you must do 10, 15, 20 tours a week of groups coming through. And thanks for being so open and willing, because everyone's fascinated by this space. Um, I'm going to throw something at you about a future look. You talked about collision-free path. Well, that's looking forward to reality. That's not reality. Everything is, going to be collision in the future. What do you see? Is this once we figure out collision free, then we start to adapt for, you know, not so perfect paths, or what's the future for that?
Yeah, I think that's an excellent question, Harold. So collision-free obviously now is a very important area of research for us, and it goes hand in hand with the ability to localize accurately, know exactly where the machine is relative to the environment and relative to the humans. Because if we are able to precisely pinpoint on where the machine is relative to all the other objects of interest without any kind of error in estimating what this location is, the ability to schedule the path for the robot and reduce the likelihood of collision becomes higher. So there is a lot of research that goes into proper localization, but there is also a lot of research that goes hand in hand in remote sensing, because obviously to be able to localize with high degree of accuracy, you have to have reliable sensing, you have to have reliable sensor fusion. So there is a lot of research that is happening in this area now to kind of enable this localization to be more efficient, reduce the likelihood of collision. But having said that, you raise a good point. Are we able to eliminate it 100% now or 5 years down the road? Maybe not, especially when you have higher uncertainty in a cluttered environment like a factory floor or a warehouse, or even with autonomous vehicles in an urban setting like in the heart of downtown Toronto when you're dealing with a corner case having to make a right turn during rush hour, and there are pedestrians, there are cyclists, there is traffic all over. So in robotics, we try to tackle the problem also through a double-edged sword. Another thing is precision control. So even if we accept that collision may likely happen in some situations, the idea is to ensure that there is a level of control and compliance. That if the robot for some reason have to touch a human or have to come close to a human, the basically that interaction in itself is safe because the amount of force that is exerted through this interaction or contact is minimal, does not constitute injury. Also, the use of artificial intelligence will allow us to create regression models and what we call reinforcement learning techniques that basically will allow the machine to learn from past experience. If there is a collision that could have been avoided, but we couldn't avoid it, we employ reinforcement learning to penalize the machine for taking that action which resulted in a collision in this particular situation, so that the next time around the robot is faced with a similar situation, it would remember ideally that the action that it took last time resulted in a penalty. Let's try something more sensible this time around, hopefully reduce the risk of collision.
Well, I'm going to throw a bit of a change at you. We were just at an aeronautics concert conference yesterday or the day before with WISA, and several different contractors, partners, industrial partners knocked on the door of Waterloo AI and said, "Can you help us with air traffic control?" And it sounds like a similar challenge that we would do with, maybe drones with Swarm and these multi drones working together in space. So instead of just 2G on a factory floor, it's now three-dimensional X, Y, and Z. You want to give a comment on applicability of your research to aeronautics?
So for us, actually, the research that we do, which can be applicable to aeronautics, basically will focus primarily in what we can offer by way of area robotics. And actually, the RoboHub, at this point in time, we don't have any ongoing project looking at fixed wings drones. So most of the research that we do is for quad rotors or hex rotors, and those typically can be used for traffic monitoring, but we've done a project in the past when we are doing scheduled delivery of parcels by using a drone to deliver parcels, or a drone that can help reroute basically parcels and how they can be delivered as fast as possible given a certain kind of traffic situation. So typically that's where we can contribute, not necessarily to the full extent of being able to create an air traffic control system, but rely on quad rotors and hex robots. And mind you, they typically have to be scheduled because most of these platforms, depending on what you have in the gimbal by way of payload, the battery life for a flight would typically range from 20 to 40 minutes. So if you want to have continuous coverage, you also have to do some sort of scheduling. One drone would have to go offline for charging, another one will take over, and you want to do this without interruption. So I think we've developed some techniques for environmental monitoring, but also for identifying the fastest route given obstacle or a traffic situation in one particular application, which is parcel delivery.
Awesome. Well, William, you've covered so many different areas. We're going to wrap up now, and I'm going to turn to you and ask for any final comments or thoughts of what you see ahead for robotics, RoboHub, your choice.
Thank you, Harold. I guess, again, it was a very interesting discussion, and thank you for all the questions. But the one thing that I want to kind of close with is the importance of the continued collaboration between robotics and the AI Institute at UW, because I'm beginning to realize now, from what I'm seeing in my role in the RoboHub, but also in terms of the research that our graduate students are conducting within the Faculty of Engineering, whether that's related to material forming or related to clean energy or related to autonomous vehicles, the importance of AI, which I see that in 5 years' time, our graduates will have to have a certain degree of competence with AI, the same way they have knowledge navigating social media and the internet. It will become as important for our graduates. Otherwise, I think in terms of being more employable and what the industry needs are, without the knowledge in AI in 5 years' time, I think that will definitely hurt their chances in being able to secure cutting edge jobs. But for us in the RoboHub, the reliance on artificial intelligence to enable us to pursue our current and future research endeavors is extremely important. And that's the reason why that in the RoboHub, we're always encouraging all of our colleagues to reach out to the Waterloo AI Institute, but also colleagues in math and computer science and other branches of engineering, forge these collaborations because of the importance that we see, the important role that AI will play to continue to help us advance robotics and get them to that level where they can be beneficial in a wide spectrum of industrial applications.
Well, that's awesome. Thanks for the pitch on Waterloo AI. That's good. Well, thank you very much today. Again, I appreciate you joining us for the podcast of Let's Talk AI, and have a great day.
You too. Thank you very much, Harold. Thank you for having me. Okay. Have a wonderful day.